All right, I think we are ready to begin. We'll let the stragglers continue to join us. Welcome, everybody. My name is Carrie Nelson. I'm with Information Insights. Our firm is providing the tech support for this evening's class. Our representative, Mindy, with CCHRC, the ones that are responsible for organizing the classes, was not able to join us tonight, so I am standing in for her. I'll try to do her justice as best as I can. But I am the one who, if you have any questions as the class is going on, feel free to pop your questions into the chat. I'll be paying attention to your questions along with our presenter this evening. But if you have any technical needs, I'm your gal, and so I will help you as best as I can throughout the evening. Before we get started and I hand it over to our wonderful instructor for the night, I just wanted to make a shout out to our sponsors that made this evening possible. So we've got generous support from the Golden Valley Electric Association, or of course GVEA, Southeast Conference, and Alaska Housing Finance Corporation. And this presentation is also made possible in partnership with our friends at NREL, National Renewable Energy Laboratory, ourselves, Information Insights, and of course, CCHRC. So with that, I'm going to hand it over to our instructor for this evening, who's going to tell you everything you ever wanted to know about heat pumps, right? Dr. Tom Marsik.
Thank you so much, Carrie. So like Carrie said, I'm Tom Marsik. I wear multiple hats, but today for this event, I'm mainly representing the Cold Climate Housing Research Center. And I want to say thank you to the organizers of this event and to the sponsors, and of course to all the participants for the opportunity to speak with you about heat pumps for homeowners. So let me share my screen here. And as I go through this presentation, feel free to ask questions right away. You don't have to wait till the end. Put them into the chat, and I'll try to address those questions as we go. So just a brief outline. So we'll start with an introduction to heat pumps and explain what heat pumps are. We'll look at a comparison between different types of heat pumps. Then we'll focus on air source heat pumps specifically and look at some special considerations for air source heat pumps. I'll tell you what we know about the performance of air source heat pumps in cold climates. I'm gonna give you some resources for heat pumps, and then I'm gonna just briefly demonstrate what kind of savings can be achieved if we combine the heat pumps with other energy efficiency measures, because obviously the biggest savings can be achieved with a system approach. We'll look at briefly at financing and incentives for heat pumps and other energy efficiency and renewable energy technologies. I'll try to draw some conclusions at the end. And at the very end, I would like to do a live demonstration of a heat pump or calculator. It's an online calculator, a very useful tool that allows you to estimate how a heat pump is going to perform in your given situation, and with that make a decision of whether you want to install a heat pump and what type of heat pump to install. Okay, so what is a heat pump? So a heat pump is a device that takes heat from a cold place and puts it into a warm place. So it's the opposite of what's happening naturally. So, naturally heat flows from hot to cold, but we can reverse it by using a heat pump. You all are likely familiar with heat pumps because you all are probably used to using a refrigerator, if nothing else. And a refrigerator is a heat pump. So, a refrigerator takes the heat from the inside of the fridge, which is cold, and puts it to the outside. That's why the coil on the back of the fridge is hot, because that's where the heat is going. Or, think of a freezer. So with a freezer inside, in the freezer, you have, say, 0 degrees Fahrenheit, and the freezer is to maintain the temperature inside the freezer. It's extracting the heat from this very cold environment, about 0 degrees Fahrenheit. So it's extracting the heat from that and putting it into a warm place. That's where the fridge is sitting. So the coil on the back of the freezer is hot because that's where the heat is going. And so we can use the same technology for heating buildings, except now we are not extracting the heat from the inside of a freezer. We are extracting it from the outside environment, which can be as cold as the inside of the freezer, or even colder. And so we are extracting the heat from the outside environment and putting the heat into the building. If anybody's interested in the details of how this works, it has a compressor, so that's why we need to supply electricity for the heat pump. And the compressor is compressing a special fluid that we call refrigerant. In this place where it goes through the compressor, it's in the form of gas. And you know what happens when you compress gas? It gets hot. And so the compressor compresses that gas, it gets hot, and sends it to the inside of the building. And now the heat is transferred from this hot gas to the environment in the building. And so as this hot refrigerant is supplying the heat to the building, it's being cooled down by that building. And as it's being cooled down, it condenses into a liquid. And then the liquid goes to the outside into what we call an evaporator. And in that evaporator, this liquid evaporates, and through the evaporative cooling, it cools itself down to a temperature that's below the temperature of the outdoor environment, which means now the heat from the outdoor environment is transferred into the refrigerant. And then it's being compressed by the compressor again, it gets hot, and the cycle continues. So it's not magic, it's just physics. And the main point here is we do need a compressor for this specific cycle to work. Now, the outdoor environment, it can be the outside air, then we call it an air source heat pump. It can be a body of water, then we call it a water source heat pump. Or it can be the ground, and then we call it ground source heat pump. The ones that are gaining the most popularity nowadays are the air source heat pumps. So that's what I'm going to mainly focus on in this class tonight. And here you can see a picture. So there's an air source heat pump here on this picture. So it's the outside unit sitting outside in the outside air, extracting the heat from the outside air. And then the indoor unit can have various shapes and forms, but this is a typical one for an air source heat pump that's that's drawing a lot of attention in Alaska nowadays, at least, is this style where the indoor unit, we call them a ductless unit, where it has no ducts. It's just the indoor unit is installed inside, typically fairly close to the ceiling, and there's warm air being blown from the outlet of the indoor unit here. But again, there can be other shapes of the indoor unit. This is just the most popular one. So what are the advantages of heat pumps? They are relatively low maintenance. They have no combustion on site. They are partially renewable because the heat is in the outside environment thanks to things like the sun. They can be fully renewable if the electricity for the heat pump is also supplied from renewable sources. And the heat pumps have the potential to lower energy costs and energy use. And that's because the efficiencies are greater than 100%. And that's why we don't really call it an efficiency. We call it the coefficient of performance. So COP is the coefficient of performance. Now, how is it possible that the coefficient of performance is greater than 100%? Well, it's again laws of physics. So from physics, we know that energy cannot appear or disappear. So the energy that we put into the heat pump in the form of electrical energy ends up in the building in the form of heat. And the energy that's extracted from the outside environment, like you see the heat pump here, it's extracting the heat from the outside environment. That energy that's extracted from that outside environment also ends up in the building. So the energy that ends up in the building is a greater amount than the amount of energy we put into the heat pump in the form of electricity. Now, how many times greater? That's what the coefficient of performance tells us. So if the coefficient of performance is, for example, a 3, or some people would say 300%, even though typically it's not stated as percentage, typically it's stated as a number, so it can be, for example, a 3. So if the coefficient of performance is, for example, a 3, it means that for every unit of energy you put into the heat pump in the form of electrical energy, you get 3 units worth of heat into the building. And why is that? It's because the one unit of energy you put into the heat pump in the form of electricity ends up in the building in the form of heat, and then 2 additional units of energy are extracted from the outside environment in the form of heat, and they also ends up in the building. So in total, you get 3 units worth of energy into the building. So for every unit of energy you put in the heat pump in the form of electricity, you get 3 units of energy in the form of heat into the building if the COP is 3, as an example. So the Alaska Center for Energy and Power did a great job compiling data on some existing installations of heat pumps in Alaska. And they looked at various types. And one of the things that they looked at is the installed cost of those heat pumps. And so here, what's on this graph on the y-axis, that's the installed cost per 1 unit of thermal output, because obviously the bigger the heat pump, the more expensive it's going to be. So if you want to compare them, a fair comparison is to compare them on the basis of the install cost per 1 unit of thermal output. And then on the x-axis, that's the size of the heat pump in terms of how many units of the thermal output. And when you look at the data, the different types of heat pumps, the data points are all over the place. And it's because there are other factors besides just the type of a heat pump that determine how expensive that installation is going to be. Other factors are things like how are we going to bring the source to the heat pump, or how are we going to distribute the heat then from the heat pump throughout the building. So while it looks like we cannot make really any conclusion from these data points here, there is actually one conclusion we can make, and that relates to this gray dot, what looks like one gray dot now here in the lower left corner, but I'm going to tell you it's actually 4 dots on top of each other. So these 4 dots each represents a ductless mini split system. So that's what you saw in the picture that I showed you before. So it's a ductless unit, and the reason that, as you can see, it's the lowest install cost out of all of these is that there is no cost to bring the source to the heat pump because it's just sitting in the outside air, so it's extracting the heat, straight from the outside air. And then there's no cost to distribute the heat because it's a ductless unit. You don't need to install a ductwork to distribute that. And because of this relatively low installed cost, these ductless mini split systems are drawing a lot of attention. And so that's one of the main things I'm going to focus on in this class, because again, the most interest is in these ductless mini split systems because of the relatively low installed cost. So the Alaska Center for Energy and Power also looked at the efficiency of these heat pumps. And so here on the y-axis, that's the average coefficient of performance. And on the x-axis, that's the temperature of the place where we are taking the heat from. So if it's an air source heat pump, that will be the temperature of the outside air. If it's a ground source heat pump, it will be the temperature of the ground. And so when you look at the data points again, and the Alaska Center for Energy and Power looked at different types of heat pumps, the data points are all over the place. Excuse me. Seems like we cannot make any conclusion about, one type of heat pump being more efficient than another type of heat pumps. But when you look at the most efficient heat pump here on the graph, there's this blue square up here with coefficient of performance of about 4.5, which is pretty impressive. It's a ductless mini split heat pump in Wrangell, Alaska. But from there, we cannot just make the conclusion that ductless mini split heat pumps are the most efficient, because when you look at the data point that has the lowest coefficient of performance, about 1.6 here, that's also a ductless mini-split heat pump. And this one is located in Dillingham, Alaska. So, so while we cannot make any solid conclusion to say one type is more efficient than other types, the conclusion that we can make from this, and again, this relates to this blue square up here, is that if we use the ductless mini-split heat pumps in appropriate situations, and we use it in an appropriate way, we can achieve very high efficiencies, which means we can save a lot of energy and energy costs with that. So that's the conclusion that we can make. Now, the question is, so what are the appropriate situations and how do we use them in an appropriate way? And I'll get to that question. So there is a fundamental challenge related to air source heat pumps, obviously. And it's that the colder it gets outside, the more difficult it is to extract the heat from the outside air. And so the capacity of the heat pump goes down the colder it gets outside. Now the building envelope is doing the opposite. So with the building envelope, you know, the colder it gets outside, the higher the heat load is for that building. And so you end up with a heat deficit, and at some point the heat pump might stop working altogether when it gets very cold outside. So at the time when you need your heat source the most, it stops working on you. So we need a backup heat source in cold climates for this reason. So that's one of the important considerations for air source heat pumps. Now, another consideration is, so what is the source of electricity and its efficiency? If you're in Southeast Alaska, for example, and so if your source is a hydroelectric power plant, it can make a perfect sense to use a heat pump. Now, if you're, say, in a rural Alaska community where the electricity is produced from diesel generators, and at the same time, rural Alaska communities often use diesel for heating. And so, you know, there's the heating oil in their oil-fired heating systems. Then we really need to ask ourselves the question: so, does it make sense to burn the diesel in the diesel generator to make the electricity for the heat pump when we can just burn the diesel directly on site in the oil-fired heating system? And when you kind of look at the numbers, if you think of a diesel generator, an efficient one would be, say, 35% efficient. Now, an oil-fired heating system is, say, 85% efficient. So 85% divided by 35% is about 2.5. So what this means that we need the coefficient of performance to be at least 2.5 for the heat pump to be making sense. Because if the COP is much less than 2.5, then the amount of diesel you have to burn in a power plant to produce the electricity for the heat pump is a greater amount than if you just took the diesel and directly burned it on site in the oil-fired heating system. So while heat pumps might make sense in some situations, they don't necessarily make sense in other situations. We need to look at all those factors. And how do we look at them? I'll demonstrate a little bit later in this presentation. So other considerations, if you're using an air source heat pump, are you going to use air-to-air or air-to-water? Again, the air-to-air heat pumps are the ones drawing the most attention, partly because of their relatively low installed cost. Now, with the air-to-air heat pumps, are you gonna use a ducted heat pump or a ductless heat pump? And again, the ductless ones are the ones that people seem to be the most interested in because of the relatively low install cost. So that's the thing that I'm going to be mainly focusing on throughout this class. So there's the ductless mini-split heat pumps. That's what we can see here on this picture, a ductless mini-split heat pump. Now, if you are using a ductless mini-split heat pump, then another question we do ask is, are you using an external thermostat or just a built-in thermostat? And the built-in thermostat, normally, when this is the indoor unit, the temperature sensor would be here. The top part is the inlet. That's where the room temperature air is being sucked in. It's warmed up, and then it's blowing warm air down here from the bottom of the unit. And so the temperature sensor would typically be up here on the inlet of the unit. Now, the temperature on the inlet can be a little bit affected by the warm air that's blowing out, because some of that by its buoyancy is making it back. So the built-in thermostat, while it's the most frequent solution, just be aware that that if you are looking for like a very precise temperature control, then there's an option for you to purchase the external thermostat that would be located, somewhere else, not directly on the heat pump. Again, if you are looking for the lowest cost solution, and that's what most people do, most people just install the indoor unit with the built-in thermostat in it. Anyway, this is just for you to be aware that the external thermostat is available if you want that. Then another consideration, of course, is what is the outside air cutoff temperature. In other words, how low can the heat pump operate as far as the temperature of the outside air? So that's an important consideration if you want to use a heat pump in Alaska. So how do air source heat pumps work in Alaska? So we did an evaluation of the field performance of some heat pumps in Alaska back in 2014, 2015. Here is a map of the locations where we studied the heat pumps, and the ones with the orange square, that's in Dillingham, Juneau, and Wrangell, those we studied in a greater detail with a lot more instrumentation on those heat pumps. And here are the results from those detailed measurements. So here on this graph, on the x-axis, that's the outdoor temperature. And on the y-axis, that's the coefficient of performance. And I see a question there in the chat. Let me read that. Will you be discussing the air-to-water heat pump and how that works? In particular, if a homeowner has a radiant all-heated boiler already installed in the house. That's a great question. Yeah, thank you for that question. So if somebody has, and that's often the case, an all-fired boiler in a home, then kind of sounds like a logical process to simply replace that with an air-to-water heat pump. And while that might work in other locations, the problem in Alaska is that typically those buildings, together with those heating systems, were designed to operate with a relatively high temperature of the distribution fluid. The distribution fluid is either water or a mixture of water and glycol typically. And because they were typically designed with while needing a really high temperature of the distribution fluid, it makes it complicated to use a heat pump. And it makes it complicated for one, in order to achieve that high temperature that the distribution system is made for, the coefficient of performance is much lower, because the bigger lift in temperature we need to make, the lower the efficiency of the heat pump. And then the other challenge is that the models of the air-to-water heat pumps available on the market often are not able to simply produce the temperature that we do need for the existing buildings in Alaska. So while it can work in some situations, in many situations it won't for this reason. There are some ways around that, and we are investigating the ways around that. One of them is that you can combine installing the air-to-water heat pump with a significant energy efficiency retrofit at the same time, where you would make your building envelope a lot more efficient. And then you can get by with a lower temperature of the distribution fluid, and then maybe the heat pump would work at that point. But again, in a nutshell, to answer your question, it's not a straightforward solution. So retrofitting an all-fired boiler in Alaska with an air-to-water heat pump is complicated. Thank you for that question. Okay, so back to this graph here. So on the x-axis, that's the outdoor temperature. On the y-axis, that's the coefficient of performance. And here we are looking at the results from the detailed monitoring that we did of the heat pumps in Dillingham, Wrangell, and Juneau. And with the coefficient of performance, we looked not only at the steady state coefficient of performance, but we also looked at the integrated coefficient of performance, which really gives the true efficiency of the installed heat pump. And to kind of demonstrate the difference between those two, now look at this series here, this with the blue dots and the black dots, which by the way is an air-to-water system. This one is in Juneau, Alaska, so a relatively warm climate compared to other climates in Alaska, even still, it's still cold, but relatively, it's warmer than other places in Alaska. So that's one of the situations where, air-to-water system was possible in this specific installation that we studied. Another situation where an air-to-water system is possible is when you're building a new home and planning, the distribution, the heat distribution system for that. That's another situation when you can design it in a way that it's going to operate with a lower temperature of the distribution fluid. Anyway, I just sidetracked a little bit to get to the previous question. But back to this data set here. So it's an air-to-water system, air-to-water heat pump in Juneau, Alaska. And now the black dots is the integrated coefficient of performance, and the blue dots is the steady state coefficient of performance. And the integrated coefficient of performance, that means the one considering all the situations that the heat pump works in, including cycles. And it does need to cycle. I'll tell you why in just a little bit in some situations. So when you look at the temperatures here from say 40 degrees Fahrenheit to like 45 degrees Fahrenheit, you can see that the black dots are on top of the blue dots pretty much. And so those two series are aligned. And it's because in this temperature range, the heat pump does operate in a steady state. That's why the integrated coefficient of performance is basically the same as the steady state coefficient of performance. But what happens when it's warmer outside? What happens is that now, even with the lowest compressor speed, the heat that's supplied by the heat pump is too much. The building doesn't need that much heat. And so what's happening is that the only way that the heat pump can accommodate it is that it cycles. It's turning on and off, on and off, on and off. And through these cycles, it's decreasing its efficiency, unfortunately. So that's why this integrated coefficient of performance, the black dots are way below the blue dots here. Now, what happens in the colder temperatures here, below, say, 40 degrees Fahrenheit also. So remember, the outdoor unit, the way it works, it's cooling itself down to a temperature that's lower than the temperature of the outside air. And so it's, when it's 40 degrees Fahrenheit, the outdoor unit, the coil on the heat exchanger on it has a lower temperature. And if the temperature is below freezing, then there's ice that's developing on the outdoor coil. And when the ice gets too thick, the heat pump puts itself into what we call a defrost mode. And the way it does, it simply reverses its operation. It takes a little bit of heat from the inside of the building and it sends it to the outside unit to warm it up, to melt that ice. And then the ice just turns into water and drips down on the ground. And so every so often, the heat pump needs to go into this defrost. And because of that, again, it operates in cycles. And that's why this integrated coefficient of performance, so that's this black series, is below the steady state coefficient of performance, which is the blue series. Another thing we noticed, and when we were doing this study, and this relates to this red and green series, it was a ductless mini split system in Wrangell, Alaska. So one thing we noticed there is that with lower thermal loading, and this heat pump was increasing its coefficient of performance. And by lower thermal loading, what it means is that, say if you have an oversized heat pump that can, deliver very high heat rate, but it's oversized for a building where the building doesn't need that much heat, then the heat pump is going to operate at a partial capacity as opposed to a full capacity. So it means it's going to have a lower thermal loading. And so we noticed that with a lower thermal loading, this heat pump was increasing its efficiency. But unfortunately, we cannot just draw the conclusion it's always going to be that case, because with this series here, so that's the blue and purple dots, that's a heat pump, a ductless mini-split heat pump in Dillingham, Alaska, we noticed the opposite, that with lower thermal loading, it was actually decreasing its efficiency. So even though it wasn't the intent of this study, this triggered an important research question that we started addressing later. I'll talk about it, about how the efficiency changes with different levels of thermal loading, because it's important to know, because it impacts things of how do you want to size the heat pumps appropriately for the buildings. Now, while I'm here on this slide, I'm going to go back to that number that I used, that coefficient of performance of 2.5. So say you're in a rural Alaska community, with diesel generation and where you're using diesel for heating buildings. So in a typical situation like that, like I mentioned, you would want a COP of about 2.5. And so as you can see, it's in the very cold temperature, it's pretty challenging to achieve the COP of 2.5. So while a heat pump might make sense in this situation, up here in this upper right corner, it's not going to make much sense here in the lower left corner in a situation like that. Now this magic threshold is a little different for different communities. So for example, in Fairbanks, Alaska, so in Fairbanks, we have a different generation mix, but when you look at the cost of energy currently in Fairbanks, Alaska, look at the cost of electricity and look at the cost of heating oil, and do the math, you'll find out that you need a COP of about 2. So not 2.5, about 2 with the current situation. It didn't used to be that way. I used to say actually that economically heat pumps didn't make much sense in Fairbanks until the war in Ukraine started, when the oil prices went up. And now, because of the current ratio of the oil prices to electricity prices, all of a sudden heat pumps are making a lot more sense in Fairbanks, Alaska. And so from the cost perspective, you're looking at COP of about 2 in Fairbanks. And from the environmental perspective, actually, are also looking at a COP of about 2. We are kind of lucky that way in Fairbanks. Those two don't always align, but in Fairbanks they do. It's because in Fairbanks, at least my understanding is that when you install a heat pump, what's gonna pick up that increased load on the grid is gonna be a combined cycle plant in North Pole, which is very efficient. And so that's what's going to be determining the extra fuel that's going to be needed and the extra greenhouse gas emissions. And when you do the math and compare it to if you are just using oil to heat your building, you'll find out that break-even point again is about COP of 2. So in Fairbanks, we are looking for a COP of roughly 2 and higher for it to be making sense. Now this series here, it's again, this was an older study around 2014. It's an older heat pump. With the heat pumps nowadays, one of the most efficient, if you buy one of the most efficient models, the crossover point with a COP of 2 is going to be somewhere around 0 degrees Fahrenheit. So if you're in Fairbanks and you have installed, if you look for a heat pump and bought some of the most efficient on the market, then you will be able to use it in a beneficial way above roughly 0 degrees Fahrenheit. In a typical situation, at least. So that's again how we are determining when it makes sense to use the heat pump and when it doesn't make sense to use the heat pump. Okay, I think I've spent enough time on this slide, so I'm gonna move on. So some general conclusions from this detailed monitoring. So the transient operation due to the on-off cycling or frequent defrost can significantly reduce performance. So we saw that when the heat pump needs to cycle, the integrated coefficient of performance is often much lower than the steady-state coefficient of performance. So optimizing the defrost controls for cold climates can increase performance. So it's an important topic for our situation in Alaska, because obviously the heat pump has to cycle because of the defrost that we need, because it operates in a cold environment. So how can we optimize them for better performance? That's one of the important research questions. And I know this doesn't affect you as homeowners as much. You don't have much control over what kind of defrost the heat pump's gonna be using. But that can potentially be one of the questions you might be asking when you are shopping for a heat pump and you are deciding between various models. So one of the things you might ask whoever you are buying the heat pump from is what kind of controls it is using for the defrost. This information is not always readily available, but if it is, that can help you make a decision. There are some heat pumps on the market that simply just have a set timer, and every so often the heat pump goes into defrost, whether it needs it or not. And then there are some smarter controls where the heat pump actually has a way of detecting if the frost, how much of the frost is built up, and tries to defrost itself only when it is needed. And also, so one of the conclusions from the general monitoring is that there are large variations in efficiency among individual models. So again, when you're shopping for a heat pump, you want to be looking at those with the higher coefficient of performance. And when I talk about the cycling due to defrost, here's just a graph that shows you those cycles. So here, like the green is the thermal output of the heat pump. And as you can see, the heat pump is running. Then it starts decreasing its thermal output. It's likely because there's too much ice being built up. And when there's too much ice, the heat pump decides to defrost itself. So the thermal output goes down to 0 while it's defrosting. It's still drawing power, so you can see here's the electrical power input. So it's still drawing electrical power because it needs it for the defrost, but it's not providing the heat for the building. And then when it's defrosted, it goes into normal operation again. It's supplying heat to the building, and this cycle then continues. Also, I talked about the cycling, the low load conditions. When it's warm outside, the heat pump, the building doesn't need much heat, and the way the heat pump is accommodating it is through cycling. So here's an example of that. Here, the green series is the thermal outputs. As you can see, it's on for about 5 minutes, then off for about 5 minutes, then on for about 5 minutes, and it continues. And again, this cycling can significantly reduce the efficiency of the heat pump. So besides the detailed monitoring, what we did, we also did general monitoring. We did this for 30 heat pumps during that study. It was a mix of ductless air source heat pumps, ducted air source heat pumps, and air-to-water systems, mix of commercial and residential systems. And some were retrofit appliances, some were new installations. Retrofit appliances means that it was a building that had a heating system installed already, and as a retrofit, the heat pump was added to that. Unlike new installations where you plan the building with a heat pump in it. And so the findings from this are that 29 out of the 30 systems provided adequate or expected heat. There were 2 repairs needed, but both were fixed at no cost to the building owners. 11 people performed maintenance on the system, but mostly simple things like cleaning the filters of the heat pump. And 12 people used their backup heating system, even though 29 had that available. So kind of the main message from this is that people are typically fairly happy with their heat pumps. So what kind of research is happening currently? Like I mentioned, the field study, back around 2014, triggered an important research question, and that's how the efficiency of the heat pump is changing with the different levels of thermal loading, and that's something we are currently studying. And I'm going to catch up on these questions in the chat here. So one is, how reliable are the vendor stated COP rating? That's a great question. So thank you for that. So the most, I would say, the best metric that's out there currently to compare heat pumps is something that's called HSPF, a heating seasonal performance factor, which is a rating that's determined on an established test procedure for the heat pumps. So all the heat pumps are tested the same way. And so that's how you can compare the heat pump models to each other, because they were all tested in the same way. So it's the HSPF, heating seasonal performance factor. And it actually relates to the coefficient of performance. It's just that the coefficient of performance is how many units of energy do you get in the form of heat for every unit of energy you put into it in the form of electricity. And with the HSPF, it's the same thing, except it's measuring the units of energy in the form of heat in BTUs versus the units of energy in the form of electricity in watt hours. So it's just relates to different units. So you can actually, if you know the heating seasonal performance factor, you can calculate the corresponding COP to it by dividing it by 3.41, and it's because it's just a unit conversion where 1 watt hour is 3.41 BTUs. But that's you don't really need to do that calculation. For comparisons, you would be looking at that HSPF, heating seasonal performance factor. It's a little complicated nowadays, though, and the complication is that's why I did not have it on a slide partly. But the complication is that the test procedure is currently being changed, and so we have the HSPF and we have the HSPF2, and the HSPF2 is the HSPF achieved using the new test procedure. So if you do want to compare heat pumps, I think the HSPF is the best metric that's available, because it's available for all heat pumps and they're all tested using this procedure. But you want to make sure you are either comparing just the HSPF or HSPF2, because if for one heat pump you have the HSPF2 and the other heat pump is just the HSPF, you cannot compare those to each other because they were achieved using different test procedures. So it's a little complicated nowadays, but it's because of the transition to the new test procedure for the heating seasonal performance factor. Okay, another question here. But with air-to-air, the variation will always be high due to changing temperatures outside. What temperature is the best planning temperature? Average during winter or other? So this, thank you for the question. So this question kind of, if I'm understanding correctly, is how do we size the heat pump? What are we planning for? And that we don't have straightforward guidelines for sizing the heat pumps. This is actually a good question that's related to this current slide. Let me explain what's on this slide, and I'll get back to that question. So this slide here shows results from our current study, where we are studying how the efficiency changes with different levels of thermal loading. It again was a question triggered earlier in the field study back around 2014. And so what we did, we tested 4 heat pumps in a cold chamber here at the Cold Climate Housing Research Center. And here are some of the results from that. So here, this first graph here on the x-axis, there's the thermal loading. So that's the percentage of the maximum thermal loading. So 100% would be that it operates at its maximum capacity. 50% would be that's only half loaded, which means the heat pump will be twice oversized for that given situation. And on the y-axis, it's the coefficient of performance. And as you can see from the result, the relationship is that if the heat pump is fully loaded and you start reducing the thermal loading, the coefficient of performance is increasing, but only to a point. And then when you're further reducing the thermal loading, the coefficient of performance starts dropping. And so what this means is that it's actually very complicated what this means. But if I simplify it, what this means is that you want the heat pump size just right. If they are too big, if they are way oversized for a situation, and you are going to be operating that here with very low thermal loading, you are going to be getting a relatively low coefficient of performance. Now, if they are undersized, which means they are always maxed out, again, you're operating with a relatively low coefficient of performance. So you want to size them just right. But it's how to size them just right is complicated. We do not have any strong guidelines yet for how to size them just right. And it's partly because this study was based on a steady state coefficient of performance, because that's the thing we were able to measure in the cold chamber. And here are some of the results from that too, where on the x-axis, that's the outdoor temperature, which actually was the temperature in the cold chamber. On the y-axis is the coefficient of performance, and the blue dots are the ones at the maximum thermal loading. So that's the ones here on the very far right of this graph. So there will be, the coefficient of performance as a function of the temperature when it's at the maximum thermal loading, while the orange dots are at the level of thermal loading where we are close to the peak efficiency, which will be here, in this region. But this coefficient of performance, it's all just steady state data. So this doesn't directly reflect the performance in the field where it's going to be cycling due to defrost. So we are currently starting a study where we are going to be looking at the integrated COP of a heat pump installed in the field. But it's just being started now, so it's going to be a while before we have the results from that. So back to the question, how to size the heat pump at the time. I understand the question in the chat. So there are currently various methods, and one of the methods simply is, so you decide, okay, I'm going to use the heat pump down to say 0 degrees Fahrenheit, and I wanted to provide the full load for my house at 0 degrees Fahrenheit, so I'm going to size it that way. So that's certainly an option to do it that way. Then other ways is to try to optimize it for the efficiency, and then we don't unfortunately have strong guidelines for how to do it currently because of the lack of data of the integrated coefficient of performance. So but back to kind of just simplified approach. Yeah, you don't want it too big, you don't want it too small. So you want to heat pump just right to get the best efficiency for your situation. And so currently you would likely be relying on the installer. So where we are purchasing the heat pump from and who is designing the installation from you, you are going to be relying on them to size the heat pump for you. And they are going to use just the best data we currently have. There are gaps, but they are going to use what's currently available to provide with their best guess of what's the best size for you. Good questions. Thank you. So another question in chat: would an energy rating provide the amount of heat needed? Yes. So that's a great point. So I'll have a slide on energy audit actually, but that's energy audit will give you a lot of things, a lot of great information, and this is one of them. Yeah, thank you for that question. Okay, so moving on here. So some heat pump resources. Alaska Heat Smart is an excellent resource. They are located in Juneau, but they do have some resources that are applicable statewide. Then, of course, the Cold Climate Housing Research Center. Then we have the Alaska Municipal Heat Pump Calculator, an excellent tool. I'm going to demonstrate how to use it in just a little bit. Then there are some national resources. Here's one from the Northeast Energy Efficiency Partnerships. Here's one from Canada. If you want to take more classes, there are more detailed classes available, like here from Qatar and Nosan Consulting Services, from Wisdom and Associates. Also, this is a useful database here, a national database for incentives for renewables and efficiency. So when we talk about heat pumps, we shouldn't forget about other things we can do to save energy, because obviously the biggest savings are going to be achieved with a system approach where we combine a heat pump with other energy efficiency measures. So here's an example. This is a super efficient building in Dillingham, Alaska. As you can see, that building has a heat pump installed. It's right here. Here's the indoor unit of that heat pump. but it's also a super efficient building envelope. It has 28 inches thick walls, so it's extremely insulated. It's extremely airtight. And so this building, the annual heating bill is a few $100s, which is a fraction of what other buildings in Dillingham pay for heating annually. And again, this was achieved by combining the heat pump with the energy efficiency aspects of the building envelope. So how do you decide if a heat pump is currently the best investment you can make, or are there other things you want to do first to save energy in your home? So like we talked about already, the one of the best ways is to get an energy audit. And I see a question in the chat. The annual cost was a few $100s, correct? So the heating bill for the home that I just showed is a few $100s annually. So a very low heating bill because of the very high energy efficiency measures in that building. In Dillingham, Alaska, which is a place with very high energy costs in general. Yeah, so just to demonstrate what's possible, when you don't rely just on the heat pump, but you focus on other things also. So again, what things to focus on? One of the best ways to find out is to get an energy rater and get an energy audit. So the energy rater is gonna come to your house and they are gonna look in the attic if you have an attic, look in the crawl space if you have a crawl space, look at your walls and windows, and take some measurements and investigate some materials. They are going to do a blower door test, which is a special test of an airtightness of your building, and they are going to process all that information and come up with a report for you. And that report is going to have all kinds of informations in it. One of the pieces of information in there is that there's going to be a list of recommended improvement options, and that list is going to be prioritized by the payback. So the most cost-effective things first. So it's again, a very valuable step is to get an energy rater and get an energy audit in order to decide what are the things that make sense to address in your home. Maybe there are currently other things that make a lot more sense than installing a heat pump. So maybe the heat pump is going to come later, and the energy audit will help you decide. So there is some financing and incentives available for heat pumps and other energy efficiency measures. There are some for renewable energy systems too. A good resource for that, again, is Alaska Heat Smart's website that I showed before. When you go to financing and incentives, it has good information about the current financing and incentives, and there are some currently coming too. So thanks to the bipartisan infrastructure law and the Inflation Reduction Act, there's funding that's currently it's being figured out how to distribute it to people in Alaska. So so stay tuned. That's coming. So another question in the chat: do sellers of heat pumps require some technical certification to sell to? I don't understand if you're asking about certification of the seller or certification of the place where the heat pump is going to go. But as far as the installer, I would definitely recommend that you look at use an installer that is licensed. And as far as the place where it's going to, I am not aware of them asking for specific documentation, but obviously you do want to install it in a building that's ready for that. If it's a building that say has significant electrical issues, for example, you don't want to add another load to it before you fix those electrical issues. So I'm not aware of them requiring specific documentation from you. but it's it certainly would be strongly recommended to address other issues first if there are other issues. Thanks for that question. Another question there: are there any different considerations that should be made if it's a new build as opposed to a renovation of an existing home? Yeah, so that's a great question. So there are certainly going to be differences when you are retrofitting versus planning a new building with a heat pump in mind. So when you're retrofitting, you're kind of stuck with what you have. So you need to make the heat pump fit that space. So you don't depending on the system you are planning, but like putting in a ducted heat pump, for example, would be difficult if there's no ductwork in the building already, for example. So you are often people use the ductless mini split heat pumps for the retrofit, and they are kind of seeing where is the biggest room with the biggest heat load, which is where they are going to put the unit, unless they want more units, and then you can put it into other places too, but then it gets more expensive. If you are already planning a building with a heat pump in mind, you are going to make the decision, are you going to go, what type of heat pump are you going to go? If it's a centrally ducted heat pump, you are going to be installing the ductwork in place. Maybe you are going to be planning on the ductless mini split heat pumps with the new building too, which would not be unusual, again, because of their relatively low cost and relatively high efficiency. But maybe you're going to plan the rooms kind of around that, have the biggest area really big, be a big area where you can heat that portion with a single indoor unit. So yes, so there are definitely going to be differences in how you're going to approach that based on if it's a retrofit or if it's a new building. I see we do have more questions here. So let me read them. For an existing home in Fairbanks with hot water baseboard heating, it appears heat pumps may not be a good choice for the whole house. However, supplemental heat for a single room in the fall and spring, like a master burner, might be helpful, especially if the cycle can be reversed and used for cooling during our increasingly hotter summer. Does that make sense? That's a great point. Yeah, thank you for pointing that out. So kind of like we mentioned, replacing the whole boiler with a heat pump in a place like Fairbanks might not be possible, or if it is, it's often going to be challenging for the reasons that we mentioned before. Likely it was designed with needing a very high temperature of the heat distribution fluid. But in that case, you can just keep the system in place and install the ductless mini split system. And then your old boiler is still going to be serving as a backup for the ductless mini split heat system. Another big challenge, obviously, that I should have emphasized earlier, in Fairbanks, if you just try to replace your oil-fired boiler with an air-to-water heat pump, that air-to-water heat pump is not going to work when it's 40 below. So you would need to add an additional heating system, and that's going to act as a backup for those situations when the air-to-water system cannot work. So with the approach I'm mentioning here, leaving the old one in place as a backup and adding something like the ductless mini split system often makes a lot of sense. And thanks for pointing out that then you can use it for cooling too. So that's another advantage of a heat pump. Is that so when we talk about the ductless mini split heat pumps, with a switch of a button, you switch from heating to cooling. So it just engages a reversing valve, and the condenser turns into the evaporator, and the evaporator turns into a condenser. So it simply changes, and it's extracting the heat from the inside and putting it to the outside. So with a switch of a button, you can use cooling, which can be handy in some situations. Keep in mind that for that, in the installation process, you do need to route the line that drains the condensate, because when you're cooling the inside air, there can be condensation. So it has the indoor unit has a tube for that condensate, and you need to route it somewhere where that condensate can go, somewhere in the drain. as opposed to just dripping on the floor somewhere that would create damage. So just keep that in mind. In the installation, if you're planning cooling, that step needs to be taken. So other questions here. I'll probably take one more question here, and I'll just, for the sake of time, I want to make sure we get to the online calculator, but then we'll get back to the questions here. So here a question: Hi, I was called away on family phone call just as I entered the Zoom meeting. Is this presentation available as a recording I could watch? It is being recorded. Yes, I believe it is. It is going to be available. Okay, thanks for the question. I'm gonna pause here with questions for a little bit, just to make sure we get through the rest of the presentation here, and look at the heat pump calculator together, and then we'll come back to the questions. So thanks for all that. Okay, so we talked about incentives. Here are just some main conclusions about air source heat pumps. So as you saw, air source heat pumps can significantly reduce energy use, energy costs when used in appropriate situations and done right. So you could see examples where the heat pumps were providing significant savings, and also situations where they did not provide savings. It was the opposite. They were actually wasting energy. Where like you saw in situations when the COP was very low and the diesel it was burnt in the power plant to provide electricity for the pump was likely a greater amount than if it was just heated with an all-fired heating system. So we don't have all the answers yet on how to do that right. So there's more research needed to gain a better understanding. Like I mentioned, the sizing of the heat pumps is an important question. Proper operations of the heat pumps also is related to how the heat pump behaves with different levels of thermal loading. So we are currently working on getting more data to understand how the efficiency changes with different levels of thermal loading to be able to answer better those questions. And of course here, the third bullet here, system approach yields biggest savings, because obviously we can get the biggest savings if we combine a heat pump with other energy efficiency measures. Lots of people and entities helped along the way, so big thank yous. We couldn't have done it without them. And let's go to the Alaska Municipal Heat Pump Calculator. So it's a calculator that was developed by Alan Mitchell of Analysis North. And like I mentioned, there are still some gaps in our understanding of the heat pump performance. But Alan just did an amazing job taking the data that exists and coming up with a tool that provides an estimate based on this data that exists. So this is kind of the best estimate you can get is based on the existing data. So so the tool is available on this website, and I'm gonna go to the website and we'll get to play together with that tool a little bit. So let me stop sharing the screen and let me start sharing my browser. Okay, so Alaska Municipal Heat Pump Calculator. So again, this is a tool you would use to decide, for one, does a heat pump make sense for you? So you can enter the parameters of your situation here, and it will provide the estimate of how the heat pump is going to perform for you. And also it allows you to then optimize how to use the heat pump in that situation. Things like at what temperature should you be turning it off when it maybe no longer saves energy when it's very cold. So let's quickly go through that. I know we are running a little low on time here, given we have a lot of questions to go through, which is great. I do encourage you to ask questions. I just want to make sure we have time for them. So I'm gonna go through this quickly. This tool does provide default values. I'm going to be mostly using those default values to save time, but then I'm certainly encouraging you to go back and use this tool and enter the values that apply to your situation. So so we need to enter the basic data here, like location, Because obviously it's going to determine how the heat pump's going to perform. So you guys tell me which location are you, which city are you the most interested in Alaska? So
Fairbanks.
Fairbanks. All right, let's put in Fairbanks. There are probably a lot of people from Fairbanks here, so that's very applicable. Okay, so let's go with Fairbanks. I'm gonna go with just the utility rate schedule, even though we could put in our manual data. And so I'm just gonna go with here, Golden Valley Electric Residential. And it's gonna automatically populate the data for that. This is not totally up to date, but it's pretty close. So I'm just gonna go with that. And it's a residential building. Okay, how big a building do you guys want?
1,000 square feet.
1,000 square feet. All right, 1,000 square foot building. I'm gonna go with the defaults: no garage, 2x6 construction, fuel type. Likely well, number one if it's Fairbanks. So I'm gonna put that one in. Let's assume it's not being used for domestic hot water, just space heating. It's populating $459 per gallon. Again, not totally up to date, but I think it's pretty close to what it currently is. So I'm gonna keep that. Efficiency of existing heating system. I'm gonna go with a standard 80%. Then it's also using electricity for like the pumps for the distribution of the heat through the distribution system. I'm going to go with that default option here. If you do know how many gallons of heating oil you are using annually for your building, then you would put it here, and it's going to help calibrate the tool even better. Here we don't know. We are just looking at a theoretical building. I'm gonna leave that blank. The electricity, for Fairbanks, we don't really have to worry about that. You would worry about it when either you are in a community that gets the power cost equalization, or in a community where you have block rates schedule, which means the price you are paying per kilowatt hour depends on how many kilowatt hours per month you are using. But again, in Fairbanks, that doesn't, for the residential, it doesn't change. So we don't have to worry about these really. And your set point, I'm gonna keep at 70 degrees Fahrenheit. So that's your thermostat setting for the indoor temperature. Let's assume it's a single zone heat pump as opposed to multi-zone. I'm gonna go with just a simpler selection method where it's just using a theoretical model with a high efficiency. Here's the HSPF, the heating seasonal performance factor of 14, which is one of the highest you can find on the market. You can actually also put in the specific model you are looking at. So you put here, advanced, and it has a database of specific models of heat pumps you could select from. I'm gonna go with the default. So I'll keep that one. Installed cost, this seems pretty reasonable. We'll be looking at in Fairbanks probably around $5,000 or so for installed single zone heat pump like that. Of course, it's gonna vary on that specific situation, but this doesn't look unreasonable. So I'm gonna keep that. Let's assume no rebate for now. Let's assume no financing. Let's assume you're just buying it yourself. Now I'm gonna keep this at heat pump turn off below 5 degrees Fahrenheit, because as you know, when it gets very cold outside, then the heat pump is becoming inefficient. So you might just be wasting energy and money when you try to use the heat pump when it's very cold. So I'm gonna leave this at 5 degrees Fahrenheit. And some people simply just to keep it simple on them, they would just turn it off for the winter. So you can also choose here to turn it off, say November, December, January, February. I'm gonna go with the defaults and just assume it's on throughout the year, except when the outside temperature is below 5 degrees Fahrenheit. And is all the building heated with one space heater? No, I'm gonna go with the default. And in that case, what percentage of the home is openly exposed to the heat pump indoor unit. So, this is a single zone heat pump. If you have a home that has multiple rooms, you're likely not going to be entirely able to heat the whole home with that single unit. But so here I'm going to go with the default that 46% is openly exposed to that one unit that we are installing in there in this theoretical situation. Now I'm going to choose here bedrooms can be as much as 5 degrees cooler than main spaces. By that, we are actually allowing some of the heat from the room where the heat pump is installed, some of the heat to go into the bedrooms because heat goes from hot to cold. So by keeping them cooler, some of the heat can go there. I'm going to go with the default option. And here I'm going to go with the option of open doors, which obviously allows the heat from the warmer rooms to go there better. And no sales tax in Fairbanks. And I'm going to hit calculate results. Okay, so rate of return 3.3%, net present value minus $500. So economically in this situation, it's not great, but it's not bad either. So we are kind of close to zero returns here in this situation, and we'll maybe play with the inputs a little more. But this is where we are. So given the initial cost of the heat pump and the savings that the heat pump is going to achieve for you throughout its life, you are saving oil. You are using more electricity because of that, and overall they kind of break even based on these values here, depending on your time value of money for you personally. So this is this net present value is assuming certain percentage as far as time value of money. Yours might be different. But really close to breaking even. And COP about 2.5. So that's pretty good. Greenhouse gas emissions. So this is based on the average fuel mix in Fairbanks, which there are things like coal-fired power plants in there. But my understanding is that what's currently happening in Fairbanks is that, like I said before, when you install a heat pump, the coal-fired power plants are already maxed out, so you're not going to be increasing the consumption of coal. You're going to be increasing the consumption in the combined cycle plant in North Pole likely. So that's the one going to be picking up the increase of the load on the grid, which is an efficient power plant. So you could override the inputs at the beginning to as opposed to the average fuel mix, put in the plan that's actually meaning picking up the load. We have done that math, that basic math. So in the current situation of Fairbanks, if you are with a COP above 2, you're actually saving CO2 emissions. So here with a COP of 2.5, you're actually saving CO2 emissions. So from the environmental perspective, this is going to be a good installation. From the economic perspective, it's going to be you're going to be breaking even roughly on that. And the results by month. So here is each month how much you are covering from the heat pump. That's the blue line. Versus from your existing system, that's the red line. So months like January, when you are rarely going to have temperature below 5 degrees Fahrenheit, which is how we said here we are going to operate it. So your heat pump's typically going to be off, and that's why not much cover from the heat pump. Unlike say April when it's warm and your heat pump is going to be covering most of the load. So these are the types of results you can find here. Also here are the savings. So every month you are saving in energy costs. So the green is the savings. The top is where you currently are, and if you install a heat pump, it's going to go down by this much. The green margin shows you how much it's going to go down. So you're going to be saving. You're going to be saving money on energy. The reason that the net present value here is negative is because it's taking into account that you're going to pay some money up front for the heat pump. And then it's assuming certain percentage as far as the time value of money to see if that would make sense in that situation. But as far as the energy costs are, you can see you are saving money with a heat pump if you don't consider the initial cost of the heat pump. So that's the types of results you can find here. And then when you have these results, like I mentioned, besides just deciding if this makes sense for you, you can also then see how you can optimize the operation of the heat pump. So for example, with this, we are using a very efficient heat pump here. And so, we chose the one with the HSPF of 14. So we might be able to actually operate it into down lower temperatures a little bit. So I'm gonna change this. Let's say instead of operating down to 5 degrees Fahrenheit, let's say we want to operate it down to 0 degrees Fahrenheit. And this will help you determine whether it makes sense for you or not. So now that we are operating down to 0, I'm gonna recalculate the results. And all of a sudden, as you can see, it's making a better sense for you. So this is a pretty good return now, and you are actually going into a positive net present value here. So in this case, we determine, yeah, it would actually make sense to operate it down to 0 degrees Fahrenheit as opposed to just 5 degrees Fahrenheit with this very efficient heat pump. So that's how you can then play with it and see if it makes sense or how to optimize the operation of the heat pump. Now, if say your building isn't 1,000 square foot building, if it's, I'm just gonna put here, at say a 2,000 square foot building, which is because now the 1,000 square foot building had a relatively low thermal load compared to the 2,000 square foot building, which means the capital cost of the heat pump had a relatively long payback because there's not that much heat that you can save with a 1,000 square foot building. Now with a 2,000 square foot building, let's see what's going to happen. Which also would, another thing that would reflect this, if we chose a smaller, cheaper heat pump for this, we are just going with the default here. So calculate the results. All of a sudden you have a much higher rate of return because now we are with the bigger building with this heat pump that we chose here. All of a sudden the capital cost is a lot more worth it, those bigger savings you're achieving. So in Fairbanks, as you can see, heat pumps are starting to make sense. And not everywhere, but where they make sense is something you can estimate using this tool. So I'm gonna pause here, and I know I promise I will get back to your questions, but are there any questions about the calculator itself while I'm on this calculator? And here is, I see on the question is the link to the calculator. It's right here. So heatpump.cf. This is your link. I'm gonna put it in the chat. Okay, so now it's in the chat also. Okay, so let me catch up on the other questions now. So let me scroll up and I think this is where I ended before. Okay, so does the outdoor unit need to be installed with a southern exposure? Not necessarily. Yeah, thanks for that question. So the southern exposure, it's not gonna change much the temperature of the air that is flowing through that. So the southern exposure does not have a significant effect. More you are looking at places like, do you have an existing overhang, for example, where you can install a heat pump, and that way you can protect it from snow, and the heat pump getting buried in a snow pile. So that's the types of things you are going to be looking at instead. And another question, do heat pumps remain more efficient than other forms of electric heat for COPs greater than 1? Yes, thank you. So thank you for that question. So normal electric heat has a COP of 1, exactly 1, which means the energy you put in, that's the energy that comes out, because it has it has no chimney, so it has no other place to go. It's not sucking anything from the outside, it has no connection to the outside. So it means the energy that goes into that that space heater in the form of electricity, there must be equally energy that comes out in the form of heat, because there is no other there's no other pathway where more heat could be coming in or where heat could be escaping. So an electric heat has a COP of 1. So with the heat pump, as long as you have a COP greater than 1, you are saving energy compared to the electric heat. But places like Fairbanks, typically people don't use electric heat in their buildings. They use things like oil-fired heating system. So that's why we are looking at a higher COP, because then that changes the equation. So in Fairbanks, again, we are looking for COP greater than about 2. Another question: can you use an HRV system to distribute the warm air? Good question. Thank you. So a standard installation of an HRV with the normal size ducts and the normal airflow from the HRV in a typical building wouldn't be big enough to distribute the heat in a meaningful way. So you can, but you would need to combine. You need to make changes to that. So you need to combine it with an additional fan and with bigger ducts, and then you could use the modified HRV system to distribute the warm air. It is sometimes done. There is a system that we developed. Actually, we call it preheat. It's a combination of words breathe and heat, where the heating system is combined with the ventilation system. But again, it does require an additional fan and bigger ducts. Another question: does a small unit exist that would be reasonable for cabin use? Currently using Toyo with wood stove backup. So smaller units do exist for heat pumps, and if the sizing of the smallest unit would be reasonable for a cabin, I don't have a direct answer to it. And it's again because some of the unknowns we have still in the performance of heat pumps, the true field performance of the heat pumps in our cold climate here. And of course, it depends on the specific cabin too. Every cabin is different as far as the thermal load goes. But they do sell smaller units, and the nice thing about it is that the smaller units are typically more efficient, and part of the reason is that they while they are smaller as far as the capacity in terms of the BTUs per hour, the heat exchangers still stay relatively big. They are smaller than the normal size unit, but still relatively big compared to the heat rate. And thanks to this, these bigger heat exchangers relative to the heat rate, they are getting higher efficiencies. So yeah, they exist, but I cannot tell for sure if they would be reasonable. I would encourage you to play with this tool here. And like I mentioned, you can select a specific model of a heat pump, and and when you change the when you choose a specific model of the heat pump here, advanced, you can find some smaller ones and put in the parameters of a cabin here and see if it makes sense for your situation. Okay, and some of you helped me answer these questions here. Thank you. And definitely you need a backup in places like Fairbanks. Yeah. So somebody put in the chat. Thank you. So when it's 40 below, there is no heat pump on the US market currently. That's going to be operating in those temperatures, and so you do need a backup heat source. Okay, and the last question I see here, and that might be the last one we have time for tonight. So that's good timing here. So is there a critical height needed between top of air source heat pump unit and overhang? So I think you are talking about the outdoor unit. So there are, there are specs for the indoor unit. So, follow the manufacturer's directions for the installation. So the manufacturer is going to tell you that you need a certain space between the ceiling and the indoor unit, and the same thing for the outdoor unit. So the the manufacturer is going to have installation instructions and tell you what kind of clearances are needed for that specific unit. Yeah, follow manufacturer's directions for that. And yeah, thanks for all the questions. This is great timing because we have about 3 minutes left. So thank you very much, everybody. And with that, Carrie, I'm handing it over to you.
Thank you so much, Dr. Marsik. That was amazing. I was just thinking as I was watching your presentation, I can't imagine having this much knowledge about any one given thing at all. So it was really amazing just taking in everything that you were talking about. And I'm really glad that we are recording this for myself because I can go back and watch it when I need to re-answer a question that I might have. So I just wanted to, I know we're at time. I am going to launch an exit poll. If everyone could, you should see it popping up on your screens now. Please just take a few minutes before you hop off. We'd really appreciate getting some feedback about the class today. I will leave up the Zoom call for a few minutes after the hour just to give you some time if folks are still filling that out. And I just wanted to make a shout out for any potential future classes like this that CCHRC puts together. They have in the past been doing kind of like a spring series and a fall series. I'm not certain if there will be a fall series, but I would say I would highly encourage following their Facebook page if you don't already. So the Cold Climate Housing Research Center. Or if you're not already part of their email list, you can go online and subscribe to that. I think some of you probably said yes or no to that in the registration. And so if you're not already part of the list, when you registered, if you said that you wanted to be, we'll get your name added to that as well. So yeah, look out for any future classes, and just thank you again, everyone, for joining. And especially thank you to those of you who were signed up for the originally scheduled class and made it to the rescheduled class. We appreciate your patience with us. And one last thing I would say, Dr. Marsik, if anyone has any follow-up questions as they think of them after tonight, what is the best way for them to, can they follow up with you directly, or is there somewhere else that you would like to direct folks to?
They can try to connect with me. Yeah, so, and my email was on the intro slide, and this is recorded, so we'll have it available. It's tmarsik@alaska.edu, and it's on the intro slide. Thank you.
Yeah. Well, with that, you're all free to go and eat your dinner if you haven't already been eating. Thank you again, everybody. I hope you all have a great night.
Thank you, everybody. Bye-bye.